Well, let us finish this discussion on structure, positions of particles, atoms or molecules, by looking into the pair correlation function. G of R we defined like this. Now, let's see its form. For a classical ideal gas, it is 1. Okay? Ideal gas. G is 1. Now, let's write GR for a system of hard spheres. This is a research area where people work quite hard to understand everything about hard spheres. Do you know what hard spheres are? Assuming the atoms are hard spheres, do they interact like hard spheres? Do they interact? Is there a potential energy for them? Of course, when the distance between the centers of these spheres are 2r, then the particles cannot penetrate into each other. That's the closest distance of approach, isn't it? And when they contact, the interaction goes to infinity. So hard spheres mean the interaction is, instead of having an interaction like this, it has an interaction like that. Something like this. So it is only repulsive interaction. At 2r it goes to infinity, otherwise it is 0 when they are further apart. Hard sphere is only repulsion, and it is almost 90% of the physics because the attractive part is very small, I told you. And this is known as the Perkusiewicz approximation in this problem. Very well known. And if you do the calculation with a potential like this, 0 if R is greater than D, infinite if R smaller than or equal to D. So that's the distance of closest approach, isn't it? If that is the UR, you can calculate GR. I have done that myself a couple of times, writing a small computer program. It's very easy. GR turns out to be, in units of D, when there's a peak, very steep peak at 1, so that this limit is 1. Something like that. What does it tell you? It says there is short range order, okay? When R equals D, nearest neighbor distance, there is a large peak, collection of atoms around. At a distance a little bit further, we have more or less two noticeable peaks. So there is short range order, but after that there is no order at all. It is completely random. So let's look at it from, I will try to draw the positions of atoms, hard spheres for you. I think you have a nice picture in your book. So it must be something like this. We have an atom at the center, some atoms around it. Okay. So touching it at D, isn't it? And there are some more atoms out. Something like this. So you have a central atom, you have the first peak at that position, and you have another peak, isn't it? You have another peak at that position. So first peak, bigger peak, closer to the atom, isn't it? Next peak, a little bit further away, like 2D or something. Huh? You have another shell of atoms, but afterwards it's completely random. Atoms all over the place. So, short range order. You can check your book about a better picture. So, that's the way hard spheres are arranging themselves because of this interaction, infinite repulsion between them. They cannot go inside each other, so there's a correlation. Is that understandable? Now you see, at those peaks, there is maximum probability of finding neighbors. There is short range order, short range, because the correlations decay exponentially. That means GR minus 1 goes like e to the minus R, something like this. That's correlation length. There is no more correlated structure after a certain distance. I told you this can be measured experimentally, and I'll give you the related quantity. But using GR, if you have GR, either from experiment or from a theory, you can calculate pressure, for example, energy. You can calculate everything. Here are some important relations. You can calculate pressure. Please check your book. It is at kBT, 1 minus n 2d kBT. Okay. Integral du dr r G of R d cube R. Okay. This is pressure, or a virial equation of state, if you like, between the relation between PV and temperature T, or internal energy NVT for the system, average Hamiltonian, if you like, and that can be written as d nkbt over 2 plus n, capital N over 2, u of r, g of r, dr. You multiply probability of finding the second particle at r with the potential energy at that distance. This gives a relationship, it's extremely important, something like this, NKB, kappa, compressibility in terms of G, this is another important relation, -1, dr, and that is related to n squared minus average n squared over average n. This is compressibility equation of state. So, as you can see, you can get the thermodynamics from G of R and interaction energy, potential energy of interaction, U of R. Now let's look at the experiment through which you can measure GR. Extremely important, I think. Such a useful quantity. How can it be measured? By doing an experiment. And what do you do to measure the structure of a system? If you are asked to design an experiment, what do you use to get the structure and information about the structure of a system? Liquid, crystal, how do you measure it? Can you measure it? Have you measured structure of any system? You didn't measure anything. Did you see anything written on in a laboratory, X-ray lab? In Hacettepe, of course, you have lots of it. X-ray. What do you think they do with X-rays? They measure the structure, isn't it? Neutrons, another way of measuring, because if you send an X-ray, X-rays are scattered from electronic charges in the system. And they show more or less how the electrons are distributed. That means more or less the structural information about the system. Where is the charge? Neutrons are going to scatter from nuclear spins, aren't they? They don't have any charge, so they have spin. So they are going to scatter from spins, and they also show an information about structure. Where are they sitting? Okay? So it is more or less X-ray or neutron scattering, a scattering experiment. Let's see what scattering does, what type of information it gives us. Well, structure of a system from inelastic scattering. X-rays or neutrons, or if the thing that you want to see is large enough, you can use visible light if you like, instead of X-rays. Huh? You have to use a wavelength which is of the order of the size of the particles. Huh? Now, here is the example of an experiment. You have the material through which you want to do the scattering, and you send something, light, in that direction. Let's take this as the K0 direction, incoming. Beam. Well, let's consider a monochromatic beam. You have a scattering, and you look at the scattered waves in the direction you put your detector. So you have a detector here, and you see how much is scattered in that direction. Huh? So what is the scattering in that direction? That means deviation from the incoming beam. So this is where you measure your scattered intensity. You are counting in some sense, huh? This is the incoming monochromatic beam, incoming beam of X-rays or neutrons. Okay, let's see and have a contact with the result of this experiment and the structure pair correlation function, information about structure of the system, how they get it. Well, the whole thing is quasi-elastic scattering. Quasi-elastic. So, inelastic part is quite weak, huh? Quasi-elastic. But of course, elastic means no energy exchange. Inelastic means there's some energy loss. Okay. Now, let's look at the scattering amplitude. From a particle at r, I, at Ri, okay, so a single particle scattering. If it is illuminated, by an incoming beam with amplitude phi 0, amplitude of this beam, wave vector K0 of the incoming beam, okay? Where is it going to scatter? Into a detector at location R. That means detector at that position, from that position. We write this scattering amplitude as phi 1k. K is the wave vector. I'll tell you why the wave vector comes in wave vector. It is incoming f of k, a function of k, e to the I k0 dot ri, e to the I k1 dot r minus ri divided by r minus ri, distance between particle and the detector. Here, k is the distance, the difference between k1 and k0. Well, k1 is the scattered wave vector. Okay? So this k is wave vector transfer. So we are really trying to describe a scattering. Well, this is scattering from one particle, but if you are scattering from a crystal or liquid, you have n particles in that system, isn't it? We have to write scattering from n particles by using this, of course. Okay? Let me write that. Scattering from n particles. Using this, I can do that. I have to do a sum. From n particles, here's the scattering amplitude, total scattering amplitude, if you like. Well, approximately phi 0 f of k. Read your book. Again, r e to the I k1 dot r. Sum over all possible positions of the scattering centers, if you like. Instead of 1, now I have to sum those coming from other particles. Is that okay? Well, scattered intensity, the scattered intensity can be written as I of nk from an m particle system as the square of this amplitude That's what you are going to count by the detector. What is the scattered intensity into your system? Now, let's keep this picture in mind. We copied it. This can be written as I n of k can be written as n times I1 of k S of k. So this is scattered intensity, scattering intensity from one particle from a single particle, a single particle all you have to do is to multiply it by the total number of particles and a function of k. That function is proportional to the sum. This function is nothing but 1 over n, average value of the sum and it is called static structure factor. Extremely important. It gives the information, it includes the information about positions of all the particles. That means structure of the system. Static structure factor. So it has the information in it on where the particles are sitting. Structure factor. Fourier transform of this gives you GR. So we are at an extremely important position. Let's write the connection between S and G. In 3 dimensions, S of k is 1 plus 4 pi n over k 0 to infinity r gr minus 1 sine k of r kr dr. So it tends to 1 as k goes to infinity. Well, in the limit k goes to 0, limit k goes to 0 of s of k is interesting. It is 1 plus n integral g of r minus 1 dr d cube r. This is kappa ideal, and that is equal to n squared over n. Equilibrium limit of fluctuation dissipation theorem. Fluctuations are related to S of k. Now, why do you think we had to have some function of wave number appearing as structure factor, which is the Fourier transform of GR, that is accessible through the experiment? When you measure S of k, then of course GR is related to that. Why do you think this must be the case? If you do an experiment, what's happening? You are looking at the structure of the function. I think she is looking at the structure of the function. How does it look as the result of experiment? How S and G looks. Why do you think we end up finding a function of k, wave number? Because all elastic scatterings or inelastic scatterings, all scatterings of a beam of light, X-ray, whatever, is taking place in energy space, in k space. Okay? They are exchanging energy. They are changing their k, the direction of propagation after the interaction. That exchange means everything is happening in k space in an experiment, isn't it? That's why structure factor as a function of k appears, but it is related to the real space structure of the system. So by doing the experiment, you get a picture of k-space picture, and you Fourier transform it to get the real space picture of where the atoms are. Okay? That's the experiment. The result, experimental results, are very similar to what I showed you. Here is the experimental result from aluminum, I think, liquid argon. I studied myself the liquid metals. So here is a GR. You can call that calculated. One is here. G of R is starting from here. Low R goes up. There's a sharp peak and oscillations around 1. and the short range order is visible. The corresponding S function, structure factor, experimental again, liquid argon, here 1, something like this, and it is of the very small values. It goes up like this, a bit broader, and second, a little bit third, and then it dies out. This is around 2 as K, 4, etc. This is R as angstrom. This is around 5 angstrom. That is about 10 angstrom. This is liquid argon at 85 Kelvin, quite a cold liquid. So these structure factors are telling us about the structure of the system, where are the nearest neighbors, next nearest neighbors, etc. So, to sum up this part, this chapter, if you like, interactions between particles introduce some correlations into the structure of the system. They are no longer completely random, but now we start seeing some structure. And there are correlations in the positions of particles. They are not randomly distributed, like in an ideal gas, but here there is a well-established order. In liquids, it is short-range order, but if I do this experiment in a crystal, what will I find? I will find a peak, a line here, another line there, and it will continue till infinity, long-range order, isn't it? Why is this broadened? Because in a perfect order, we know what the next nearest neighbors are. Nearest neighbor positions we know, next nearest neighbor positions we know. But in liquid, some of the atoms displaced a little bit closer to the atom at origin. Some are a little bit away from their normal positions, isn't it? There is some disorder, but it doesn't kill the short-range order. So even in a liquid, you have order in the atomic structure.